How many people made some progress on this proof? Seems like a lot of people were just waiting for me to give the answer, just staring at the screen and not writing anything down. Did anyone make any progress? Did anyone try anything? What can we try? There's only a certain number of theorems we have, right? And we just taught congruencies. Did anyone try anything?
No, we were listening to music.
You got to be able to do both, right? Okay, Paige.
I tried using the division algorithm to reduce the GCD of 2 to the a minus 1, 2 to the b minus 1.
Okay. And then, so you divided 2 to the a minus 1 by 2 to the b minus 1 and got some remainder?
Yeah.
Okay, what did you get when you did that?
I got the remainder as 2 to the a minus b.
Okay. Okay, so you did 2 to the a minus 1 divided by 2 to the b minus 1. Okay, how did you do that? Oh, okay, because these are both just, well, this is not 2 to the a minus 1. This is 2 to the a minus 1 like that. So how did you divide, work with that?
I sense that I've made an error in my proof. Okay.
Did you do difference of squares or something? You assumed that a is even?
No, I just made an arithmetic error.
Okay, yeah. Anyone else? Did anyone else try anything? Henry.
I note that 2a minus 1 is the same as 2 to the 1 plus 2 to the 2 plus 2 to the 3 all the way to 2 plus 2 to the a minus 1.
Okay, someone tried to do that in the last class too. And then what did you get from that?
Oh, no, I'm still working on it.
Oh, okay, okay. So that's a cool property that Zach from the previous class mentioned as well. But just like him, it didn't get you anywhere, I suppose, in terms of proving this. Right? Okay, let's go. So the GCD of this and that divides this and that, right? If it's the GCD of this and if it's the GCD of A and B, then it divides A and it divides B. So the GCD of this divides 2 to the a minus 1, and that's what I've written there. Now, how can we represent this in terms of congruencies? I taught you A is congruent to B mod M. What does that mean by definition?
M divides A minus B.
M divides A minus B. So if I have A is congruent to B mod M, then M divides A minus B. So, what are we going to write next over here? Grayson?
That should give us 2a is congruent to 1 mod the thing on the left.
Yeah, so 2 to the A is congruent to 1 mod the GCD.
Yeah.
Okay? Because by definition, if we have A is congruent to B mod M, that means M divides A minus B, which is what I have there. Okay? These two statements are completely equivalent. It's if and only if. It's just by definition that this follows from that. There's no math done here. Okay, now let's raise both sides to the power x. We're used to doing this, right? We had 3 squared to the power 2,000 in the last class. So here we just have 2 to the a to the power x, 1 to the power x. Have I gone too fast for anyone? We can do the exact same thing for 2 to the b minus 1, because GCD of 2 to the a minus 1 and 2 to the b minus 1, it divides 2 to the a minus 1 and it divides 2 to the b minus 1. So we have the exact same thing for 2 to the b minus 1. And we've just used a y instead of an x. There's a reason for that. We could have raised both sides to the power x, but I raised both sides to the power of y, because now I can multiply 2 to the ax and 2 to the bx, and multiply 1 to the x and 1 to the y. Now, if you've tried to fill in the gaps between my lectures by looking at the course notes a bit, they've actually stated a theorem which we've been using all along when we've been doing these congruence manipulations. One of them is that if A1 is congruent to B1 mod m, and A2 is congruent to B2 mod m, then A1 times A1 times A2 is congruent to B1 times B2 mod m. Okay, you guys saw that? You saw that? Yeah, we were using that all the time, right? Because we were saying this, we have this 3 squared times 3 to the 1,000 is congruent to, I have the 3 squared is congruent to 1 mod m, and 3 to the 1,000 is congruent to 2 mod m, so I was just multiplying them together. So we were using that all along, and now we're doing sort of the backwards, we're doing the same thing backwards. We have 2 to the ax and 2 to the by, we multiply them together. So we have a1 is congruent to 1 mod m, and a1 is congruent to b1 mod m, and a2 is congruent to b2 mod m. So we have a1 times a2 is congruent to b1 times b2 mod m. Let's simplify this. We have 1 to the x times 1 to the y, that's 1. On the left, we have 2 to the ax plus by. Now you've got the proof done? Now you've got the whole thing? So what's the final step we're going to write? Well, I'm going to write a couple more steps, but... Well, so now, why is it that this statement is true based on this right here? Okay, you've already answered one, so let's get someone else. We have that 2 to the ax plus by is congruent to 1 mod m, where this is m. Why does that mean that this huge thing divides 2 to the GCD of a and b minus 1? Why is that the case? Philip.
Well, since x and y are any integers,
Yeah.
arbitrary, we can set them to be the certificates of correctness for
Yeah.
a and b, such that ax plus by is equal to d, where d is the GCD, so therefore you have 2 to the d minus 1. That is 2 to the d is equal to 1 mod this, which means that 2 to the GCD minus 1, that the GCD of, that the left side divides the right side. So
Okay.
the right side divides the left side.
Yeah, I wouldn't say 2 to the d is equal to 1 mod, I would say it's congruent to 1. Okay. So just watch, you put 3 lines instead of 2 on the exam. You don't put that it's equal. All right, so we have ax plus by for arbitrary integers x and y. That is equal to the GCD of a and b. Remember the GCD characterization theorem? You have ax plus by equals d. So in this case, and d is what? It's the GCD of a and b. So we have ax plus by equals d. And in this case, d is the GCD of a and b. If a and b were coprime, it would be ax plus by equals 1. So you'd have 2, but you would just have 2 to the 1. But because the GCD of a and b can be any general number, it doesn't have to be 1, it's just equal to d. We have ax plus by equals d. D is equal to the GCD of a and b by the theorems from chapter 6. Now, okay, now you did say everything all the way up to the end, but let's see if someone else, Nola?
Which theorem would you cite for this? Like, would you put like something beside that step?
Okay, so you want to, so you can do it in a number of ways. I mean, you can throw in Bezout's identity and stuff. But one thing, I'm just thinking on the spot. What am I going to think if I don't have much time to think on the exam? Okay, I want to prove that something is the GCD. So then it would make sense to use the GCD characterization theorem, because I want to prove that something is the GCD, right? So I have GCD characterization theorem says that D is the GCD if and only if I can find x and y such that ax plus by equals it. That's the GCD characterization theorem. What's the GCD characterization theorem?
Don't you also have that whatever your d is has to divide, divide b?
It has to divide a and b.
Yeah, isn't that also part of it?
Okay, but the GCD of a and b does divide a and it does divide b by definition.
Yeah, and so then the last part is the important part that you said.
The last part of the GCD characterization theorem is the important part, and that's the part that I said.
Yeah, the as plus bt.
Yeah. Yeah. Well, the GCD of a and b divides a and it divides b by definition. So if I write down GCD of a, any two integers have a GCD. And so whatever that GCD is, it divides a and it divides b. So that part is done. I didn't even have to say that. But by the GCD characterization theorem, if I can find an x and a y such that ax plus by equals it, then I can write it like this. All right? I think that is that okay?
Yeah, I just have another question.
Yeah.
I was wondering like how you thought to add like to multiply by like the power of x and the power of y.
Oh, well,
Like,
yeah. So you just need practice. I mean, every question is different, right? There's no. It's not like you memorize the product rule and you use that same rule every time. Here, you want to everything we want to prove is completely different, right? So there's only so many strategies that you can use, though. You can multiply things like when dealing with congruencies. Often we take something, we raise it to a power, because you can raise both of these sides to the same power. You can add and subtract the same number from both sides. You can multiply, you can use there's a congruence theorem where it's like if A1 is congruent to B1 mod M and A2 is congruent to B2 mod M, then A1 times A2 is congruent to B1 times B2 mod M, and so that's what I used here. So there's only so many theorems you can use to say 3 or 4 properties of congruencies, and you try each one. That's my best advice. There's no procedure for like, when I see this, I will think to do this. Even for me, like if it came up on the exam for me, I wouldn't know immediately what to do. I would try doing various things until it works. And that's just the nature of how proofs work, okay? You want a shortcut to doing proofs. Alexander the Great was told, there's no shortcut, okay? For kings, yeah, you have a shortcut. You don't have to wait on the 401 on the traffic. You have your private jet, but there's no shortcut to geometry. There's no shortcut to proofs. All right, so what can I do in my last line? Because I haven't exactly stated that GCD of this and this divides this minus this. Yes, Mercedes.
You could say like by the definition of congruence.
Yes.
GCD 2a and then 2b minus 1 divides 2 GCD AB minus 1.
Yeah, so the definition here, I have A is congruent to B mod M. By definition, M divides A minus B. So I have N divides A minus B. Got it? Okay, this is a very famous GCD proof, and apparently it was also taught in the ALIES section in Math 135 for software engineering, because one of the students in my last class said he already knew the answer to this because he looked at his friend's course notes. So that was apparently taught in the last class by Ali. Also, if you looked it up on Google, 2 to the A minus 1 and 2 to the B minus 1 and GCD of A and B, you're going to find that millions of people have asked this question on the Math Stack Exchange in the past, okay? Here they have 2 to the A minus 1 and 2 to the B minus 1. Here they have 2 to the M minus 1 and 2 to the N minus 1. Here they have 2 to the D. Here they have x to the a minus 1 and x to the b minus 1 instead of 2 to the a and 2 to the b. Here they have b to the x and b to the y. Remember, this works not just for 2 to the x and 2 to the y, but it also works for 5 to the x and 5 to the y. This works for any base b. So here they have a to the n and a to the m. In fact, here they have GCD of b to the x minus 1, b to the y minus 1, b to the z minus 1, b to the p minus 1, b to the q minus 1 equals b to the GCD of x, y, z, p, q, everything. So there's generalizations of this theorem. This is a really famous theorem, okay? And we can even ask you on the exam some interesting questions like this. Find the GCD of 2 to the 60 minus 1 and 2 to the 50 minus 1. Look, the powers are not even the same, but you can play around with your x's and y's, right? This is visible from the back. Henry, Jimmy, is this okay? Even this, you can see the exponent? Okay, Henry says he can. Jimmy, is it okay? All right. Okay, here we prove that if a to the 170 is congruent to 1 mod n, then a to the 111 is congruent to 1 mod n. So there's a lot of varieties of this type of question. It's a good one to know for the exam. Okay, let's get going. Now, I had some slides that I showed the last class. There's some people in this class that don't want me to show the Mobius quiz results anymore, so I'm not going to, don't look at these numbers, you don't have to look, but I just wanted to point out that I'm very proud of everyone because we beat the software and the computer science classes again. This time by 2%, not just by 1%. Okay, there was one class that beat us this time, but that was the software engineering class. Software engineering, it's even harder to get into software engineering than CS, okay? Did you guys know that? So software engineering, they're doing 6 courses right now, okay? They have Math 135, Calculus, Linear Algebra, so 3 maths, then Physics, Classical Mechanics, CS 137, and Introduction to Software Engineering. So they have 6 courses this term. 7 next term, and then 8 in their 2A. But one of those courses is just a seminar, so that's okay. All right, so next. There is a Mobius quiz tonight, so don't forget about that. Assignment, you've already submitted, good. Readings, so 8.1 to 8.4, that's pages 122 to 133. If you haven't read that yet, it won't take long. I've already covered it all, but you've got to still read it to fill in all the gaps, because I was using all these modular arithmetic rules, but I would rather give you the practice, because people find it hard to find what the last digit of 7 to the 3333 is. So I spent time teaching you how to do that, but all the minor details about like whether this is true for all integers m or just positive integers m, those minor details you can read slowly the course notes to get through that, but it won't take long. The next thing, pages 122 to 148. It's on the Math 135 schedule on Learn. It's supposed to be next week, but it's worth getting a head start, and I told you the reason why last time. Okay, so in the course notes, if you look at the course notes, we have here 8.6 is congruence classes and modular arithmetic. 8.5 is nonlinear congruences. Do you all remember how to solve a nonlinear congruence? So if I have x squared plus x is congruent to 2 mod 8, you know how to find the x? You just make this table, right? You do x mod 8, that's, x can be 0, 1, 2, 3, 4, 5, 6, 7. If I write down 8, that's just equivalent to writing down 0. Mod 8 is the same thing. X squared, you do x squared mod 8, same thing. X squared plus x, you just add up these things mod 8, and then you find which columns give me a 2. I want to get 2. So there's 2 different columns here where if x was equal to 1 or x was equal to 6, then I would get that x squared plus x is congruent to 2 mod 8. And likewise, I did the simpler example, 4x is congruent to 6 mod 10. Again, you can do it in a table. Why can you do it in a table? Can you always do it in a table? Pardon me? Why are you saying no? If you have a really large modulus, then it'll take you forever to do the table. Because we had a small modulus, 10, and here 8, then you can just make a table instead of doing the extended Euclidean algorithm. Okay, we also did divisibility by 11, which some of you already knew. We did show that this huge number is divisible by 11. We did divisibility by 3. We did the last digit of 7 to the 3333. We did 2 to the 22 times 3 to the 33 times 5 to the 55 mod 11. And we answered the question, what day of the week will it be 3 to the 47 days from now? Okay, so we've done all of that stuff, but it's worth it to read through everything just to make sure you fill in the gaps. Now, week 10 is supposed to be congruence classes and modular arithmetic. Fermat's little theorem, Chinese remainder theorem, splitting the modulus, and integer polynomials and the rational roots theorem. Okay, I'd like to do more examples. The majority of the class said they wanted me to do more practice exam questions. I have gone through pretty much all of the course notes now for 8.1 to 8.5. And the majority of the class did say that they wanted me to do more examples from final exams and stuff. I see people even nodding their head right now. Okay, but there's not much sense in doing examples until you've learned all of this, okay? 8.6, 8.7, 8.8. There's just not much sense in doing more examples until you've learned that. Because why practice proving things without these theorems if on the exam you'll be allowed to use them? So on the exam, there's going to be questions, and you'll be allowed to use the Chinese remainder theorem on the exam. And you'll be allowed to use Fermat's little theorem. So why practice doing final exam questions using basic GCD theorems when on the final exam you'll actually be able to apply the Chinese remainder theorem, right? It's just, that's not what you're, on the exam you're going to have all this stuff. So I think we better learn all of this stuff before we start, because I could give you practice problems and you're going to try to prove it using DIC, when really you could prove it using congruencies. Or like you could have proved this warm-up question using DIC and some basic GCD theorems maybe, but I showed you how to do it with the modules, and that was easier. It's a one-line So I told you the software engineering class, Ali taught it for the software engineering class, but apparently he taught it using induction. So he did, he allowed A to be fixed and then did it for all B or something. I don't know, but this is a one-page proof. It's even faster than writing down the induction hypothesis in the base cases. So once you know modular congruencies, this proof just becomes simpler. And so I'd like to teach everything before we start doing more practice problems, okay? So why practice proving things without theorems if on the exam you'll be allowed to use them? So the faster we get there, the sooner we can start doing practice exams more seriously and realistically. By realistically, I mean like this is actually what it's going to be like in the exam. You already know all the theorems. Now let's try to do this really hard problem. Okay, so let's try to get through all this stuff as soon as we can. 8.6 is congruence classes in modular arithmetic. Okay, if I went through how many people think I went through 8.1 to 8.5 too fast? So that's the stuff I showed you, the last digit of 7 to the 3333, and what day of the week will it be 3 to the 47 days from now? Solving the nonlinear congruence, x squared plus x is congruent to 2 mod 8. You do it with a table. You think I did it too fast?
Yeah.
Okay, yeah, anyone else? Okay, 2 people, yeah, 3, 4, yeah, okay. There's a few people. Now, tell me what I need to go through more slowly and I will do it. So if there's specific things, there's people that just always put up their hand and say, go slower, all the time. But there's got to be something specific that I went through too quickly. You looked at the course notes, you've got to do your part. You look through the course notes and this thing is actually confusing. Then you let me know and I will go through it. Because I know some of the parts of the course notes aren't explained so well. Okay, but first, read the course notes to fill in the gaps. Don't just rely on me. Ask on Piazza. There's 1,300 people helping you out there. Ask at the office hours. Go to the online tutorial center. And if you really think that you learn better what's in the course notes, if you learn what's in the course notes better if lectured rather than reading on your own, then you can look at the lecture notes of some of the other instructors too, right? So you guys have seen like Anton's lectures are online. Are Jerry's lectures online? Jerry's are available? Jerry Wong? Okay, so you have Jerry's, you have Anton's, you have Shane Bauman's. And a lot of those guys, they're not doing assignment tips, they're not doing previous exam problems, but they're doing the content, right? So if you want to, if you don't like the course notes, reading it, then there's I'm not going to repeat the same stuff that other instructors already have made available. Okay, but be careful. Lectures don't tend to be as refined as the course notes. One mistake could be very costly. So they might have put a P instead of a Q, and then or they might have said it correctly, but you wrote it down wrong, and then you're studying for the exam with the wrong stuff. Okay, the course notes don't have mistakes like that, at least not as many. Okay, so just another thing. If you did look at Jerry Wong's lecture notes, he did congruences lecture 18. Today's lecture 25. Okay, he did congruences lecture 18. He did Fermat's little theorem, lecture 21, Chinese remainder theorem, lecture 22, cryptography, lecture 23, complex numbers, lecture 24, and polar form of complex numbers, lecture 25. So today he's like 7 lectures ahead of us. So if you think I'm going through 8.1 to 8.5 too fast, then you can try to sit in his class. It's going to be 7 times as fast, right? Okay, now I'm going to do congruencies now. Okay? So, I already did congruencies. I'm going to do congruence classes. So I'm going to teach you what that is. Now check this out. 6 is congruent to 6 mod 11. Right? Because 11 divides 6 minus 6. Okay, 11 divides 0. Good. Minus 5 is congruent to 6 mod 11. If you were in my office hour, you remember this, right? We did a modular congruence proof in my office hour, which started over here and it went all the way up to there. And at the end, I got minus 5 mod 11 for the answer. I asked the audience, give me a random integer and a random exponent and a random modulus. And they said 7 and 2,132 and some other, and they just gave me some random numbers. And it took from there to do and I got minus 5 mod 11. And then I said, check it in Wolfram Alpha. What is this huge number mod 11? And Versano said, it was 6. Not minus 5. And then I was like, okay, well that's all right, because minus 5 is congruent to 6 mod 11. But that's not so obvious to everyone, right? So 11 divides minus 5 minus 6. So 11 divides minus 11. 11 also divides 6 minus 6, which is 0. So 11 divides 0, 11 divides minus 11. 11 divides a lot of things. 11 divides 17 minus 6, right? 28 is congruent to 6 mod 11. Minus 16 is congruent to 6 mod 11. There's a lot of things that are congruent to 6 mod 11. So when working mod 11, I'm going to define a set mod 11. That set is going to be denoted 6 with square brackets around it. That is the set of all integers that are congruent to 6. Okay? So all of these integers, minus 16, 28, 17, minus 5, they're all part of the same congruence class. It's a set of integers that are all congruent to the same thing, in this case 6. So, now, formal definition. The congruence class modulo m of the integer a is the set of integers such that x is congruent to a mod m. And we denote it with an a and square brackets around it. Okay? That a with square brackets around it has no meaning if we haven't defined the modulus yet. But once you've defined the modulus, so mod m, mod 11, mod 2, whatever it is, we can define square brackets a like this. For m equals 4, modulus is 4. We have these 4 congruence classes, 0, 1, 2, and 3. So in the congruence class 0 in square brackets, we have 4, 8, 0, 12, 16, all of the multiples of 4. In the congruence class for 1, you have 1, 5, 9, 13. Anything where the remainder is 1 when you divide it by 4. Okay? Now why don't we have 5 congruence classes here? Vihan.
The congruence class of 5 would just be congruence class.
Can you say that a bit louder?
Congruence class of 5
Congruence class of 5.
would just be congruence class of 1.
Congruence class of 5.
Would just be equivalent to the congruence
Class of 1. What about the congruence class of 4?
0.
0. Okay, yeah. So the congruence class of 4, you're just going to have the same integers. It's going to be the same set. You're just going to be labeling it as 4 with square brackets, which is the same as 0 with square brackets. And in fact, if you did that, the graders will probably get confused. They'll think you made a mistake. Why did you write 4 in square brackets when you could have just written 0 in square brackets, okay? Why would you write 444 in square brackets when you could have just written 0? They might get confused. You might lose marks, okay? So we're going to define Zm, okay, the integer symbol subscript m, to be the set of m congruence classes. So we go from 0 up to m minus 1. We don't write down, when we're working mod 4, we don't write down 4 with the square brackets around it. It's equivalent to 0 with square brackets around it. So you're going to confuse the graders if you start writing 4 with square brackets around it. Only go from 0 to m minus 1, okay? So this Zm, that is the set of congruence classes. Each of these is a congruence class. This is also a set of sets, because 0 in square brackets is a set, 1 in square brackets is a set. These are all congruence classes. Those are sets of integers. So the integers mod m, this is a set of sets, a set of congruence classes, and each congruence class is a set. Now we can define addition and multiplication on these sets. So the congruence class of A plus the congruence class of B is equal to the congruence class of A plus B. And likewise for multiplication. So we're reteaching you adding and multiplying again, but now for a different, we're no longer adding and multiplying numbers, we're adding and multiplying congruence classes. Okay, and remember I told you the term modular arithmetic. That's what my former student Hugh Binney said on the game show. That's how he knew that 100 days from now it's going to be Friday. And he said that he knew that because he used modular arithmetic. So what I was showing you before, all that congruent stuff, that was just baby steps. That was just congruencies, right? Like A is congruent to B is congruent to C. Okay. Now when we start doing adding and multiplying of these congruence classes, that is what is known as modular arithmetic. Okay? So I'll give you 1 minute. Try to do the adding of mod 4 I want you to try to do the adding of all these different congruence classes. So it shouldn't take that long. I'll give you 1 minute. Congruence class of A plus the congruence class of B is the congruence class of A plus B. Yeah. You've done? You done? Oh, you forgot your pencil.
Are you ready?
Now I'm thinking right now. I've got it in a dimension. X is 4, it starts back to 0.
You're done? Yeah. What was the 3 plus 3?
3 plus 3, 2.
Okay. Oh, this is easy. I didn't even need to give you a minute. These guys don't even need to write it down. How did you know that so fast? Don't say modular arithmetic. You read the course notes?
I'm gonna need like grade files, like I was like about to go in details, to be honest. Didn't have time this week.
Oh, but you still got this. Okay, well, okay, so 1 minute is up. There's some people that already did it, so. How many people got 0, 1, 2, 3? 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. Everyone got that? Okay, everyone got that 1 plus 1 is 2? Everyone got that 1 plus 2 is 3? And what's 1 plus 3? Yell it out. 0. Okay. What's 3 plus 2? 1. Okay. And 3 plus 3? 0. 2. Okay. Sorry. Okay. Multiplication. I'll give you 30 seconds this time. Try to do this one. All right, all done? Everyone got 0, 0, 0, 0. 0 times anything is 0. 1 times anything is itself. 1 times 3 is 3. 1 times 2 is 2. Everyone got that? Okay, what's 2 times 2? 0. What's 2 times 3? 2. What's 3 times 3? 1. Excellent. Okay, you now know modular arithmetic. Okay, now, who knows what this is called? I have a plus 0 equals a. So, what is 0 called in this case? I have a plus 0 equals a. What is 0 called? Vihan.
Additive identity.
Additive identity. How did you know that? How did you know that? Pardon me?
Grade
Grade 8. Are you kidding me? That was in Calgary?
8.
India, okay. So, additive identity. Identity is you do something to the identity and you get back what you started with. Okay? So, here, I added the additive identity to A, and I got back what I started with, just A. Okay. So, what's the negative A over here? What's the negative A called? Now that you know that that's called the additive identity, what's the negative A called? They didn't teach you this in grade 8? Yeah, when did they teach you that?
Grade 8.
Grade 8? Oh, so his grade 8 teacher was better than yours. I'm joking. Okay, so minus A, that's called the additive inverse. And I made a mistake here. This is not supposed to be a 0, that's supposed to be minus A. Okay? So I take something and I add something to it, and I get the additive identity. That means that I've added the additive inverse. So minus A is like the inverse of A. because when I add minus a to it, I get the identity. Oh, I already gave you that one away, sorry about that. So, okay. Now, if I'm mod 4, what's the additive inverse of 2?
Minus 2 from that.
Minus 2, but that's wrong, isn't it?
Yes, it would be 2.
It would be 2, because minus 2 is equivalent to positive 2 when we're talking about congruence classes. Okay, now I have a times 1 equals a. What is the 1 called? Try to remember from your grade 8 class, okay? I know it was a long time ago, but you all learned this, right?
You just showed it. Like
Yeah.
multiplication.
Okay, well, okay. I thought that since I showed it, people would be able to. Now this should say 1, not 0. So this is multiplicative identity. I take something, I multiply it by the multiplicative identity, I get back what I started with. Now, what would the 0 be called in this case? I have a times 0 equals 0. What would the a be called? What would the 0 be called?
Multiplicative inverse?
So, when I multiply a by 0, do I get back a? So 0 is not the inverse of a. I'm taking a, I'm multiplying it by 0, and I'm not getting the multiplicative identity. I'm not getting 1. So the multiplicative identity is 1. If I take a and I multiply it by something and I get the multiplicative identity, then I have the multiplicative inverse. But here I'm taking a, multiplying it by 0, and I'm getting something that's not the multiplicative identity. So the 0 is not the multiplicative inverse in this case. So for any a, the b, such that a times b equals 1, is the multiplicative inverse. Okay, so if a times b equals 1, not 0, but 1, then b is the multiplicative inverse. We can call this a to the exponent minus 1 to denote the inverse. Got it? Okay, so solve for x in with the modulus 11, solve for x. I have congruence class 8 times congruence class x equals congruence class 4. Got it? Yeah, what is it? No, it's not 7. 8 times 7 is 56. 56 minus 4 is 52. Well, that is divisible by 4, isn't it?
52.
No,
52.
Divisible by 11.
Pardon me?
You would take 52 removed of that.
Yeah.
Yeah. So, okay, Philip?
It's 6.
It's 6. Yeah, because 8 times 6, what's that equal to? 48, and 48 minus 4 is 44, which is divisible by 11. Sorry, when I saw the 56, I was thinking mod 4, and I was like, yeah, 52 is divisible by 4. However, we're working mod 11 right now. Good for spotting that, Philip and Vihang both. Okay, so we have a Diophantine equation right here. 11 times an integer plus 8 times an integer equals 4. That's what we're trying to solve here, right? We're trying to basically multiply 8 and everything else in the congruence class of 8 by some integer or any other integer in that congruence class, such that when you multiply these two integers, when you multiply 8 and x together, you get 4, and then what you get when you subtract these will be divisible by 11, so it will be some multiple of 11. Now, because these are congruence classes, I could have put what's something equivalent to 8 mod 11? Negative 3. Okay, yeah. So I could have put negative 3 here. I could have put 19 there. Okay, because these are classes. There's an infinite number of Diophantine equations I could have written down, but this is the simplest one. I just take the numbers straight from there, right? 8, 4, 11. So I'm doing the same thing as I did last time. I'm solving a congruence relation, like 8 times x is congruent to 4 mod 11. I'm basically doing that. But I'm saying that by solving that, I'm actually solving an infinite number of congruence relations. Because 8 could have been anything in that congruence class. 4 could have been anything in that congruence class. And it works. It's just Diophantine, it's just basic Diophantine principles, right? Vihan?
I think I missed it, but what is the Z11?
Okay. What is the Z11? So who remembers what Z11 means? No one remembers what Z11 means. And I know Arnav and Philip know. How about, I remember, okay. Nitya? Okay.
It's the set of all congruence classes in Mod 11.
So the set of all congruence classes, mod 11, yeah. So who asked that? That was Vihan, right? So you got it now? Okay. So it's the set, the congruence class 0, the congruence class 1, the congruence class 2, all the way up to the congruence class 10. The set of congruence classes, mod 11. All right. So when does A have a multiplicative inverse in Zm? Under what conditions does A, the congruence class A, have a multiplicative inverse? Grayson?
Would it be when we have AB is congruent to 1 mod M?
AB is congruent to 1 mod M.
So the set, like, the multiplicative inverse would be congruence class B, such that A, congruence class A times congruence class B is the congruence class 1.
Yeah, but there's a much easier way of saying this, isn't it? See, okay, you're saying... And I think the answer goes up if I take too long, so I'm trying to do this fast. So you're saying that we have A times B. Oh, this chalk is good. Is this Nagahama chalk? Oh, okay. There's this chalk in Japan, which like all the mathematicians are like fighting over because that company doesn't make it anymore. And now it's like $1 million per piece of chalk or something. No, it's not $1 million, but apparently these mathematicians just have boxes and boxes of it in their closet. You've heard of this?
Yeah.
Yeah? Okay, so this is equal to 1. Isn't that visible? That's better than the other chalk, isn't it? Okay, A times B equals 1, right? And then what did you do? You said 1n plus 1 times n plus A times x equals B. Is that what you did?
No, I'm just saying that we have a multiplicative inverse if there is a congruence class B such that that's true in the module.
Yeah, but then you said something about A being congruent to B or something?
No, it'd be, you could just use your multiplication for congruences
Uh-huh.
to, like, A and B is congruent to 1.
Uh-huh. Yeah. Now here we had congruence class of 8 times congruent class of x equals congruent class of 4. I'm keeping this chalk. I'm going to put it in here. That's congruence class of 8 times congruent class of x equals congruence class of 4. So I took the modulus, I multiplied it by an integer, and then I added 8 times x, where x is an integer, and said that's equal to 4. Now if I want 8 times the inverse equals 1, by definition it's going to be 8 times that thing equals 1, right? So I'll have a 1 here, and then I'm going to have a Diophantine equation where the left side equals 1, right? And that means that we basically have the GCD of A and M equals 1, right? So that's the condition when the GCD of the A and the modulus equals 1, then we have a multiplicative inverse. Got it? When is the multiplicative inverse in Zm unique? Vihan?
I think always.
Always. Very good answer. Very good answer. Because we have AS plus MT equals 1. That's what, here we have A times X equals 1. That's the formula that you get when you're dealing with the multiplicative inverse, showing that X is a multiplicative inverse. So, or another way to say that is AS plus MT equals 1. What is the general form for the the solutions for S? So all solutions, all values of S that satisfy this are going to take a certain form. Versano.
If you just solve for S like rearranging the equation, then you get S is equal to 1 minus MT over A.
MT, what if 1 minus MT over A is not an integer? Because you're dividing by A. You're looking for Diophantine. Everything here, we're just looking for integer solutions. If you want continuous, you go to calculus. You go to Math 137. Eric?
Can you create the equation in terms of n for this one, or no?
In terms of M?
Yeah, like n.
N. Where's N? There's no N. There's N.
Like just like we do in regular Diophantine equations, when you solve it, you take it in terms of n. So
What's N?
n could be any possible integer. So
Uh-huh.
if there's
And what's the general form for that any possible integer? Philip has his hand up for a while.
S naught plus N.
And what's N equal to?
N is an element of the integration.
Uh-huh. Anyone else want to try?
That's,
Okay, so if I have one solution, S0, S will be equal to S0 plus M over GCD of A and M. That's supposed to be an M. So S0 plus M over GCD of A and M. So any solution, any S that satisfies this, any integer S that satisfies this is going to have the form S0, which is some solution, plus M over the GCD. Okay, so S is the congruence class. So you might be wondering, oh, why is it unique when there's a million different values of S that work? There's an infinite number of values of S that work. So why is it unique? If there's an infinite number of solutions to this, then why is the multiplicative inverse unique? You solve this to get the multiplicative inverse. Grayson?
There's only one S that falls between 0 and M minus 1.
So S in brackets happens to be a set of all S's that work. And this S in brackets is unique. So S plus 1 in brackets is not going to work. S minus 1 in brackets is not going to work. Anything in this S is going to work. So there's a million different values of S that will solve that Diophantine equation. But S in brackets is unique. There's only one set of all. This set is unique. Okay? So if I change this set, it's not going to work. So the multiplicative inverse is unique. Okay, for all prime numbers P and non-zero elements A in ZP, the multiplicative inverse exists and is unique. Why is that? Yeah?
Because every integer except 1 in P is going to be co-prime to P.
Because a prime number will be, the GCD of a prime number with the modulus is going to be, the GCD of the prime number with A is going to be equal to 1. So here, we said under what conditions does A have a multiplicative inverse? It's if the GCD of A and M equals 1. So if I'm working mod P, where P is a prime, then GCD of A and P has to be 1, because it's a prime. So that theorem is a corollary. It's just a result. It's just one step after the we proved the previous thing, and then just one step after that, you just say this is a special case of that. If your modulus is prime, then GCD of A and P is equal to 1. So the multiplicative inverse exists and is unique. If possible, find the multiplicative inverse of 5 in Z10. Try to do that. Philip?
It won't be 1 since the GCD of 5 and 10 is 5, then 5 is not equal to 10.
Yeah, so we said that the multiplicative inverse exists if the GCD of A and the modulus equals 1. Now we're doing 5 modulo 10. The GCD of 5 and 10 is not equal to 1. So there isn't a multiplicative inverse of 5 when working mod 10. All right? Now, if possible, find the multiplicative inverse of 5 in Z42. Now, first you check, does the multiplicative inverse exist? Well, GCD of 5 and 42 equals 1, so there's definitely a multiplicative inverse. It's just a matter of finding it. Okay, this is my last example anyway, so yeah, Grayson, you found it?
I think so, it should be 17.
Yeah, 17 is right. So you just apply the extended Euclidean algorithm. So you have a Diophantine equation here. Remember, we have modulus times x plus the congruence class, the number in the congruence class times y equals 1. And you just solve that Diophantine equation. And that's the last example of the day. You could try the next example at home. That's just the system of congruence class equations, but I don't expect you to be able to do this one. In the last class they tried it, we ended a little bit earlier there, but no one was able to do it. But anyway, the course notes gives you the answer for that one. Okay, it's a long solution, but it's a good one. It practices everything. Modular congruences, congruence classes, divisibility, GCDs, Diophantine, everything in one question right here. Solve this system of equations in Z11. Very good question right there. Okay, so we're done modular congruence classes. I just want to say, next is Fermat's little theorem. I just want to say, we just did 4 pages of the course notes today. Read 8.6. I would say to read that thoroughly, because this congruence class stuff is the hardest part of Math 135, I would say, the concept itself. So the proofs are going to get hard when you know Fermat's little theorem and Chinese remainder theorem and all that, because then you're going to have 25 different theorems that you can use to answer a Math 135 final exam question. But in terms of concepts, congruence classes, they're a little bit tough, because the congruence class is a set. We're dealing with sets of sets, right? That ZP, that's a set of all congruence classes, and each congruence class is a set. And we're adding these and we're multiplying these, and what I did in class you might just be following it, but I think you should fill in the gaps by just reading these 4 pages. And if you haven't read 8.1 to 8.5, you don't need to, because you don't need to know all that stuff. This 4 pages is independent of that, okay? So you can just try to read those 4 pages to catch up. And then you can catch up later on these ones if you want, if you haven't had time for that. And most exercises in 134 to 138, I've already done them in class, so you don't have to spend too much time on the exercise. Just try to get a feel for this A in square brackets. Try to get used to that, okay? I'm not going to do another class on that. Jerry did it in one class. I did it in one class. Friday, we'll do Fermat's little theorem and the Chinese remainder theorem. Monday, we'll do splitting the modulus. And then we're ready to start seriously preparing for the exam. Then, once we have that, pretty much any question that's not about complex numbers or polynomials, we can actually do. So any question on the final exam, we can start doing those once we get Fermat's little theorem and Chinese remainder theorem out of the way. So we're going to try to do that as soon as possible. So try to read this congruence class stuff. It's just 4 pages, but if you can do that, then it'll help you get a better feel for congruence classes. Okay? Thank you very much for your attention, and I'll see you on Friday.